Okay, good question. Technically a week from when we finished that, but that's not a hard and fast thing. That's a convenience thing. If you need more time, take your time, but here's what I say. I want it turned in before we finish, before I'm ready for the next test. And when is the next test? At the end of 4.8. So we do have some time, quite a few pages to go before then, but please get it in before we're ready for the next test. We're just finishing 4.5 today and starting 4.6, so you've got time. But when you finish it, go on and get it in so I can go on and work on grading it. And that way also, if you run into issues with this test, we can maybe satisfy those issues before I give you the next test so you don't wind up missing the same thing twice. Okay, so that's why I say get it in before the next test. And the sooner before the better. All right, thanks. Good question. Any others? All right, now we're not quite ready for 4.6 because my mark on the page had me that we didn't get time to do the vocabulary, and my memory is same thing. We just finished that trigonometric model of the water, depth of the water, right at the end of the class last time. So let's do the vocabulary in 4.5, page 3.304, top of page 304, 4.5 exercises. 4 questions here. Fill in the blank. One period of a sine or cosine function is one blank of the sine or cosine curve. So one period of the function represents one blank of the cosine curve. Now I can probably think of several words that would fit there, but I know what they're looking for. Anyone have an idea? If you turn back to page 297, if you do have a book, the very first paragraph under basic sine and cosine curves, they talk about a sine curve and similarly a cosine curve, but then they talk a little bit later is the one period of the function is one cycle of the sine curve. It goes through one complete cycle before it starts repeating itself. So that's what they're asking for there. It's sort of a nebulous word. So that was cycle. The next one you should be able to answer without too much prompt. The blank of a sine or cosine curve represents half the distance between the maximum and minimum values of the function. What is that called? And I don't know if you picked up, I said the blank. If blank was the word, I would have said the blank. By saying the blank, that indicates the word they're looking for starts with a vowel. The blank of a sine or a cosine curve represents half the distance between the maximum and minimum values of the function. Anybody? Okay. If you flip back one page to 303, the summary of the amplitude, you got it. Bingo. Way to go. Oh, we can't say bingo in Alabama. Okay, never mind. All right. Number 3. The function y is equal to a sine of bx minus c. For that function, c over b represents the blank blank of one cycle of the graph of the function. It's actually more than one side, the entire function. C over b represents the blank blank, the blank blank. Remember, this is the one I don't use c over b. I factor the b out of the parentheses, and then what's left I call c. What they're calling c over b, I call c. That is called represents the phase shift. You got it. All right. Number 4. for the function y is equal to d plus a cosine bx minus c, d represents a blank blank of the basic curve. Anybody? Okay. They don't have this under the summary that I see it, so you would have to go back to page, goodness, where is it? Oh, 302, just below the middle part of the page. I can think of two different words. The first word's going to be the same no matter what. The second blank could be two different words at least. D is a vertical nobody's home. Either vertical translation or a vertical shift. Either one of those would work there. All right, and I think I made all the assignments of the homework exercises, didn't I? It's just any of the odds from any of those groups. And I think we did them all. Now, was there anything else I needed to say about those? I can't see anything now. Maybe one thing. Okay. At the bottom of page 307, there is a project here on meteorology. So if that's an interest of yours, that could be, if you can find anything on that, potentially a paper topic. Now, hold on just a minute. I'll need to close my door. Hold on. Okay, quite a production there, sorry. My wife just got back from physical therapy, and I talk so loud it's rather disturbing. So when I'm here by myself or just me and the dog, I can have the light on. I mean the door open. Okay. All right. Any questions then on 4.5 before we move into 4.6? None? Okay. Chapter 4 is still trigonometry. We're going to get through it soon. Okay, I can't advance the slide until I click on the slide. Okay. 4.6 is graphs of the other trigonometric functions. Remember, we've done sine and cosine. Those graphs look almost identical. They're just shifted one from another. That's all. Otherwise, the shape's the same. The domains and ranges are the same. Everything's the same. The other trigonometric functions, tangent, cotangent, secant, and cosecant, those have some characteristics different from sine and cosine. Okay? Primarily this, domains. That's going to be the biggest difference. Tangent and cotangent also have difference in periods, okay? But that's a sort of a minor thing. The main thing is the difference in domains. So our objectives here are to sketch the graphs of the tangent function, the cotangent function, the secant and cosecant function, and then toward the end they're going to throw in another type of function. This is called a damped trigonometric function. Be sure you put the P in there. Okay, never mind. Okay, so anyway, those are our objectives here. So let's start with the graph of the tangent function. And we start by thinking about what is a tangent function. It's a sine over cosine, y over x. Now here's the problem. Cosine, if you remember, can be 0 at certain locations. It is 0 at certain locations at your half pi's. Y over x. Y over x, x can be 0. And it is 0 at your half pi's. Remember sine and cosine? They were y over r or x over r. R was never 0, ever. So therefore they're defined everywhere, all real numbers. But tangent, because it's y over x, because it's sine over cosine, the x and the cosine take on take on 0 values. Doesn't matter about being negative. 0 values you can never divide by 0. So that's the big difference, one of the big differences in the tangent function. Okay, we know that the tangent function is odd. Yeah, how do we know that? Earlier I think we talked about it. That is, the tangent of minus x is equal to minus the tangent of x. That means whatever it's doing on one side of 0, it does the opposite on the other side of 0. Consequently, the graph of y is equal to the tangent x is symmetric about the origin. That's what it means to be odd. Sine is odd, okay? So in that way, it's sort of like sine, but not quite. Okay, you also know, and this is what I was talking about, that tan x, tangent of x, is the sine of x divided by the cosine of x. And since the cosine of x does occasionally have a value of 0, you have to exclude. Tangent is undefined everywhere that cosine is equal to 0. And where is cosine equal to 0? Cosine starts at 1, but at pi halves at 0, then it goes down to negative 1 at pi, but it comes back up to 0 at 3 halves pi. So every half pi, I call it, it's not really every half pi, but every value of pi that's divided by 2, those are where cosine is equal to 0. And since cosine is equal to 0 there, tangent is undefined there. Here are two such values, x equal plus pi over 2, which is about positive 1.5708, blah, 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 irrational number, or minus pi over 2, which is negative 1.5708, blah, 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 blah. Okay? Those are two values where tangent is undefined. And where a tangent is undefined because it's going to, function is undefined where it's going to 0, those represent vertical asymptotes. If you remember that from pre-calculus algebra, vertical asymptotes. Tangent is going to have a bunch of them. Every place that you have a, what I call a half pi. Okay? Now this shows a graph of, let's start in the middle here. When x equals 0, tangent is 0. Why? Because sine over cosine, sine is 0, 0, cosine is 1, 0 over 1 is 0. Okay. At pi fourths, we're skipping the other, at pi fourths, sine and cosine are the same values. That's on the diagonal line there. That's on the identity function line. Okay. So sine and cosine have the same value, root 2 over 2. So that then tangent will be the ratio of root 2 over 2 over root 2 over 2, which is 1. Now, pi fourths is something on the order of 0.76 or something like that. Let's jump up to 1.5. Okay? Wow. If you pull out your calculator, get it in radian mode, and do tangent of 1.5 radians, you'll see it's a big number. Let's get a little bit bigger number, 1.57. Goodness gracious, look at that one. That goes up to 1,255.8, and that's rounded, okay? If you went to pi halves, you remember pi halves was 1.5706. If you went to pi halves, everything goes bonkers because it's undefined. It's getting infinitely large as you approach pi halves. 1.57 is close to pi halves, but not quite there. If you get a little bit closer, it goes even higher. A little bit closer, it goes even higher. But it never can reach pi halves. It's undefined. If you go in the opposite direction, tangent of minus pi fourths, well, sine of minus pi fourths is negative root 2 over 2, but cosine is positive root 2 over 2, so the ratio of them is negative 1. So tangent, because it's an odd function, is going where it went positive 1 here, it goes negative 1 there. Then you go to the same negative 1.5 and you hit the same value here, but negative 14.1. Go to negative 1.57 and you get to negative 1255.8 approximately. And then as you keep going closer and closer to negative pi halves, that the tangent function is going infinitely negative, undefined, going toward negative infinity. As indicated in the table, tangent increases without bound as x approaches pi halves from the left, decreases without bound as x approaches negative pi halves from the right. So those are the vertical asymptotes, minus pi halves, positive pi halves, going to negative infinity here, positive infinity there. So here's how it looks. The graph of y is equal to tangent x has vertical asymptotes at all your half pi's. At negative half pi, 1/2 pi, 3/2 pi, negative 3/2 pi, 5/2 pi, negative 5/2 pi, 7/2, and on and on and on. All the half pi's, okay, is 0. And at all the whole pi's, okay, I like the sound of that. 0 pi, I don't like the sound of that. 0 pi, 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, it's always 0 because sine is 0 there. It's undefined at the half pi's because cosine is 0 there. Okay, now what does this result in? Tangent repeats itself not every 2 pi like sine and cosine do, but its period is pi, because you see it repeats itself every value of pi. Between negative pi halves and pi halves is pi. Between this 0 and that 0 is pi. Between this 0 and that 0 is pi. It repeats itself as a period of pi. Sine and cosine, 2 pi, tangent, and later we'll see cotangent, pi. They are the only two trig functions with periods of pi. Now, domain, all values of x's except your half pi's. Pi halves plus n pi, where n is any integer, positive, negative, or 0. Okay, so your half pi's. The range now, this is the only trig functions also, go from negative infinity to positive infinity. Everything in between is a legitimate answer to a tangent function. Domain, everything except those half pi's. Vertical asymptotes, that's where, with a woozle wasn't, where the domain is not defined, that's where your vertical asymptotes are at all your half pi's. Symmetric about the origin, whatever it's doing to the right of the origin, going up, to the left of origin, going down. To the right of origin over here, down, left of the origin over here, up, by the same amount. There is how tangent function looks. A pretty straightforward. Okay. St. Mary's, Pennsylvania. I don't believe any of my students are calling from there, so I'm not going to answer that one. Excuse me just a second. The phone just keeps ringing and ringing and ringing. Any questions on how the tangent function looks? Okay. Now, I want to point something out to you I don't think the book does a good job of. Okay? And that's this. They've said it earlier, but then they don't use it. Okay? Trying to find my pen here. Well, if I use the right end of the pen, it would work better. Okay, there we go. So obviously we have some key points here. The period is pi. Again, divide that period into fourths. So your intervals are going to be pi fourths. Now they don't mention pi fourths. Okay? So let's start with minus pi halves, vertical asymptote. Minus pi fourths, what's special about that? besides the fact that this thing is in the way, what's special about that? That's where you're at -1. And we showed that before. And at 0, it's 0. At pi fourths, it's 1 again. Okay? And at positive pi halves, it's the vertical asymptote. So again, your intervals are important. But with tangents, it's not maximum minimum. This has no maximum. It has no minimum. But the intercepts are there, but those are just 1 point. Where you had max or min before, we now have vertical asymptotes. Okay, well, that's not quite true, but for whatever. Okay, for sine it was. Okay, but the other part here, that's where you're at plus or minus 1. Okay, so to me, those are easy points to plot. Why leave them off? But they don't mention that. But the intervals of pi fourths at the edge of the interval versus asymptote, right in the middle of the interval, an intercept, halfway between each of those, +1, -1, -1, +1. Okay, so I include, same as we did before, divide the period by 4, and you get your interval, and your intervals will be asymptotes, intercepts, or +or -1. Now, later we'll see another important feature of that. We'll get to it in a minute. Okay, moreover, because the period of the tangent function is pi rather than 2 pi, the vertical asymptotes also occur at those half pi's, where the domain is not defined. Those are your vertical asymptotes, okay? Where n is any integer, pi halves plus n pi. Not 2n pi, n pi, because the period is pi. The domain of the tangent function is a set of all real numbers, other than where your vertical asymptotes are. Okay, the range, though, set of all real numbers. We saw that on the last slide. Now, sketching the graphs of this, and here we have our A tangent B x minus c. Again, I like to pull the B on the outside and make it x minus c on the inside. My c is their c over b. Okay, it's similar to sketching the graph of this, in that you locate the key points to identify the intercepts and asymptotes. No maximum or minimum. But that additional point that you have here, okay, now here's where I'm going to introduce it. Okay, sine and cosine have relative maximum, relative minimum. They define your amplitude. A is related to the amplitude. Absolute value of little a is your amplitude. Tangent obviously has no maximum, has no minimum. It doesn't have an amplitude. However, that a is still important, and this is what the book leaves out. In a function where a is not equal to 1, so it's been stretched vertically or shrunk vertically, the plus or minus a is what goes in at your quarter pi's. This will be at minus a. This one is just tangent x, so the b is equal to, I'm sorry, the a is equal to 1, so that's -1 and +1. But at all the others where you do have an a in there, this at your quarter pi's, you're going to be at minus a and plus a. So there you can use the a not as an amplitude, but where you cross plus or minus 1. No, I'm sorry, where your quarter pi's are, and they'll be at plus or minus a. Okay, so sketching the graph of this is similar to sketching the graph of that, in that you locate the key points to identify the intercepts and asymptotes, and also the places where you're at plus or minus a. Okay, that sort of takes the place of the maximum or minimum. It's where the function is plus or minus a, and those are your quarter intervals. Plus minus quarter interval, minus a quarter interval. The rest of them same. B relates to the period. The only difference is period is pi, not 2 pi. So your period is pi over b, not 2 pi over b. And then your phase shift is, the way they do it is c over b. I factor out the b, and then it's what's left in here is I call c. Okay. So two consecutive vertical asymptotes can be found by solving those two equations. This is how the book loves to do it. To me, it's just easier to do the way I described. You know, pick your key points, and where they were the endpoints before, they're now vertical asymptotes. And that's what they're saying here. And this is listing your vertical asymptotes, and the midpoint between those two consecutive vertical asymptotes is your x-intercept. And then the midpoint between a vertical asymptote and the midpoint is going to be plus or minus a. Why won't they say that? It makes sense. It helps you graph the functions properly. Okay, so the period, again, I divide the period into 4 pieces. One piece is going to be vertical asymptote. The other end is going to be a vertical asymptote. In between is going to be a 0, and in between those are going to be plus a, minus a, and plus a. It just keep the same practice going. Now it's minus a and plus a rather than max and min. Okay. So the amplitude of the tangent function is not defined. So let's use the a to determine where you are at your quarter periods. Why don't they say that? I don't know. After the plotting the asymptotes and the y-intercept, plot a few additional points. Hey, guess what? Plot your plus or minus a at your quarter pies. If they just said that, they'd have it knocked. Finally, sketch 1 or 2 additional cycles to the left and right. You got it done. So let's do one. Okay, here is y is equal to tangent x. Okay, and I started the same way I always did. What's your a? Anyone answer that? What's the a here? Anybody? Coefficient of tangent? 1. Excellent. Way to go. Okay, what's your b? You could have written this as 1 times the tangent, there's your a, of 1/2 x. That's the same as this. So your b is? B is 1/2. Okay. The c, of course, here, what did I write? B is 1/2. I was going on to the next. C is 0 because you have no phase shift, and the D is 0. You have no vertical shift. Okay, so I just wrote those in because I usually do. Okay, A doesn't tell us amplitude. Tangent doesn't have amplitude, but A tells you your value plus or minus the value at your quarter period. So let's get to do with the period. B has to do with the period, and the period is your normal period, and for tangent and cotangent only, that's pi divided by b. Okay, but your b here is 1/2, and dividing by 1/2 is the same as multiplying by 2. So this first example, I sort of hate they did this to you. They make it the period 2 pi. Don't think tangent period is 2 pi. The reason it's 2 pi is because that b is 1/2. Okay, so what do I do once I have the period? Then I get the interval. The interval is that period divided by 4. In this case, 2 pi over 4, which is pi halves. That sounds a lot like a sine or a cosine, but that's because your b was 1/2 here. So let's draw our axes here. If I can find my pen. There you are. Okay. So there's your vertical axis, supposedly. There is supposed to be a horizontal axis. It's not very horizontal and not very straight either. And let's do our intervals. And each interval is 1/2, so we'll do the pi halves, I'm sorry. These will represent our intervals. We're going to have plenty of them. Now remember, we try to keep the x-axis sort of scaled the same. Mine's not very well done that way. But the vertical axis we can scale any way we want to, and I like to do at least plus or minus a. So we'll make this 1, 2, 3, 4, 5, 6, and negative 1, 2, 3, 4, 5, 6, maybe even a 7 down there. Okay? Now, this will be our quarter interval, which is pi halves. Our interval, which is and this will be pi. This will be 2 pi. This will be 3 pi. This will be 4 pi. This will be minus pi halves. Minus pi. Minus 2 pi. Minus 3 pi. Minus 4 pi. This is the one I have a minus 5 pi. Don't have it on the other side, but that's okay. And this will be, where are you, pen? Come on, pen, show up somewhere. There it is. Okay, this will be 1, 2, 3, 4, 5, and 6, and this will be a negative 1, negative 2, negative 3. I got these a little closer together. Ignore that, because I didn't think I had it that far out of line. Okay, okay, let's do our key points. Okay, tangent starts at 0. If I can find my 0, there it is. It starts at 0. Now, half a period is 2 pi, half a period to the right, vertical asymptote. Half a period to the left, vertical asymptote. Okay, and each period is 2 pi, so from 2 pi there will be another vertical asymptote and another vertical asymptote. Another vertical asymptote. If I can find my pen, there it is. And this one actually has another one, this one here. I didn't space them too well, so that came out an extra one here. Okay, what's exactly in between your vertical asymptotes? Your intercepts. Okay, so at 2 pi, at 4 pi, at minus 2 pi, if I can find my pen, there it is, at minus 4 pi. Now, what do we do with those quarter intervals? That's your plus and minus a. But a is 1, so here on the right it will be at plus 1. Here on the left it'll be at minus 1. And you see I didn't space them too well. So this will be at minus 1. This will be at plus 1. This will be at minus 1. This will be at plus 1. This will be at plus 1. This will be at minus 1. This will be at plus 1. This will be at minus 1. So here's what it looks like. Comes up here, kind of goes through a little jig here, and goes up here. Then repeats itself every period. Every period starts at negative infinity, goes through your plus and minus a and your intercept, and goes to positive infinity. That's what your tangent function looks like. Okay? I don't have a vertical asymptote there. Key 1's in the way, but anyway, we could have it. There is a graph of that. Looks just like the other, except what have you done here? It's a non-rigid transformation. You multiply by 1/2, multiply the x by 1/2, which of course is a vertical stretch, because everything you do with x with the horizontal axis is backwards. So a 1/2 here is a horizontal stretch. A 2 there would have been a horizontal shrink. A 2 in front here, in front of the tangent, in front of the, wherever my pen is, there it is. A 2 here would have been a vertical stretch. A 1/2 would have been a vertical shrink. Okay, Get the general idea? All right. I'm going to come down here and clear my ink so you can see how they did it. I just learned to do that recently. By solving the equations, oh, now this is how they do it, and it's perfectly fine, but yeah, it just seems a little ludicrous to do it this way. Put the thing here, x over 2, first let it be minus pi halves, which would be your first vertical asymptote would be, plus pi halves would be the next one. Solve those and basically multiply each equation by 2. You have x equal minus pi, x equal plus pi. Those are your vertical asymptotes. Okay? So they will occur there. So the period is the difference between them, which is 2 pi. Negative pi to the left, negative pi to the right. That's a total of 2 pi. Between the vertical asymptotes, plot a few points. And why do they say a few points? Including the x-intercept, midway between the vertical asymptotes, which will be at 0, you have your intercept, 0, and then midway between those will be your minus a and your plus a. A here was 1, so it's minus 1 and plus 1. They do it, they never say it. Why won't they say it? I don't know. All right, so there's the graph of how that looks. Now, because you have a horizontal stretch, you have doubled what would normally be your period, doubled your distances to your y-intercept, your vertical asymptotes, and distances between there. And here are your plus a and minus a. So right there, they did it without saying it. Okay, that's example 1. Now, right after every example, of course, there is a checkpoint. Please do your checkpoints soon after class so you can review that. Now, we're going to do example 2. It's not on the slide set, so let's back up a slide and do example 2 on our whiteboard. Okay, now I've got to do some maneuvering here. You can't see it, but I have a taskbar that's sitting right in my white space, and I have your names on the white space there on the right, so I'm going to move the whiteboard as far to the left as I can and as far up as I can to give me maximum white space. Okay, there we go. So here's example 2. Sketch the graph of y is equal to, I think I'm in a different color. Let me go back to black. Okay. Y is equal to, that was left over from last class, minus 3 times the tangent of 2x. Okay. And folks, I started just like I always did. First, that question I asked myself is, what in the world is my a? The a here is negative 3. Now, sine and cosine, that would relate to amplitude. The absolute value of that would be your amplitude. Tangent does not have an amplitude. But this means the a represents plus or minus your quarter period. So remember that, plus or minus your quarter period. Okay. Next question I ask myself is, what in the world is b? Here b is equal to 2. What is b related to? Just like before, b is related to period. The period for tangent is equal to the normal period. Remember, tangent and cotangent have normal periods of pi. This would be period of pi over 2, because pi divided by b, the period divided by b, pi over 2. Okay. I then go on and do my intervals here. My intervals is 1/4 of the period. So I'm going to write it this way: 1/4 of pi halves, and that will be pi eighths. Okay, and then I ask myself, does it have a C? The answer is no, so there's no phase shift. Does it have a D? And the answer is no, there's no vertical shift. Okay, so we're back to our basic trig function, except we have a different period, different typical tangent function, different period, different interval, and different A. Okay, including a minus sign, which we'll deal with. Okay, okay, these are going to represent my intervals: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, negative 1, 2, 3, 4, 5, 6, 7. Whoa, wait a minute, here's Courtney. Good deal. Let's let Courtney in. So the bottom part of our alphabet, we got one of the three people down there in. Still missing Alondra and Sharika. Okay. Courtney, if you're here now, it sounded like you came in. We're in Chapter 4, Trigonometry, Section 4.6, Graphs of Other Trigonometric Functions, and we're on page 309, and doing example 2, which is not on the PowerPoints, so we're having to do that on the whiteboard. And we just got set up here. We found our A was -3, or the function is y is equal to -3 tangent 2x. The A is -3. Tangent does not have amplitude, but that A still has meaning for us. That's the value plus or minus A is at your quarter periods. Remember that. B is 2. That still relates to period, but tangent and cotangent have periods of pi rather than 2 pi. So the period is pi divided by B. Your B here is 2, so the period is pi halves. Your interval then would be 1/4 of your period, which would be pi eighths. C was 0, meaning no phase shift. D was 0, meaning no vertical shift. So I was in the process of drawing out the tick marks on my line here, and that's what I will continue doing here. These will represent our intervals, and up here we'll represent our vertical values. And typically I make sure I have at least my plus or minus A as a tick mark. I'm going to continue vertically having plus or minus 1. So let's fill in here. The intervals are pi eighths, so this will be pi eighths. This will be 2 pi eighths, which is pi fourths. This would then be pi halves here. 2 more over would be pi halves. And 4 more over, because it took 4 to get to here. 1, 2, 3, 4. That will be pi. And 1, 2, 3, 4. I need 8 of them. I don't have 8. Back on the negative side, we got negative pi eighths, negative pi fourths. And by the way, I didn't tell this class, I told the last one, happy October. And I look outside my window, it hardly looks like October, except I see just a few leaves just beginning to change. So we're going to have fall. We're in fall right now. What reminded me of this, I just saw an oak leaf come drifting by my window, meaning, yep, fall is getting close. So this is minus pi halves. Has nothing to do with what I was just talking about. Go over 1, 2, 3, 4 more, and you get minus pi. And you could go over another 8, which is off scale. So vertically, let's go 1, 2, 3, 4, 5, 6, and negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. How did I get so many down here? Negative 7. Doesn't matter. I'll write down negative 8. We're not going to use it anyway. Okay. Now, how do we begin this? Tangent at 0 is 0. just like sine is, because tangent is sine over cosine. This drives me nuts. I try to put a circle there, and it takes me back to a text mode. So I have to do a lot of little marks there. Okay, now what are we going to do? Go to write half a period. Well, a period is pi halves. Half a period would be pi fourths. So half a period to the right will be a vertical asymptote. You know what? I kind of like to put vertical asymptotes in red because that tells you can't touch it. You can't cross it. You can't go there. Okay? And on the left, half a period is minus pi fourths. Ooh. So now we'll do one period apart. And a period is pi halves, so there's pi halves. Remember, our marks are eighths, so 4 tick marks, 4/8 makes 1/2 pi. Okay, so that's 1, 2, 3, 4. So there's another vertical asymptote here and here. 1, 2, 3, 4 over. That's why I do my intervals here, because it makes everything so relatively easy to do. 4 here, 1, 2, 3, 4 here. And there's another vertical asymptote going up here and down here. And 1, 2, 3, 4. My last one on this graph will be something like that and something like that. So there's my vertical asymptotes. Now let's go back to black and do my intercepts. They're going to be smack dab in the middle of those vertical asymptotes, which will be 2 over, so that makes 1 right here. Smack dab in the middle of here and here, and I don't have 2 over there, so it's somewhere over there is another one. Now we use our A, plus or minus A. Now since A is 3, minus 3, that's where we begin. So go over that first interval and go down to minus 3. That means on the opposite side, because tangent's an odd function, it'll be a plus 3 here. A plus 3 here, a minus 3 there. A plus 3 here, a minus 3 there. A plus 3 here, okay. A minus 3 here, a plus 3 there. Look at that. That was to be a minus 3 down here. Oh, that was to be a plus 3 up here, and it didn't show up. So let me try it again. Right there, a plus 3. This will be a minus 3 down here. And a plus 3 up here. And a minus 3 down here. Okay, so this time it's heading this way. Okay, and it's coming from your positive infinity here down through your quarter period, and it'll do this every time. Every time. Oops, whoa, 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 here's Azora. She must have had to leave and come back, because I already had her here. I'm certain. Yes, I did. Okay, so glad she's back. Here's another vertical asymptote going from positive infinity here. Oh, get back up there. Okay. Coming down here, swirling through there, and coming down there. Same thing here, coming from up there, through there, and down there. Again, going from up here, through that one, through this one, and down here. I got off across my vertical asymptote, which I should not do, and it continues on down here somewhere. There's what it is. Well, the negative flips it across the x-axis, so that's why it looks backwards here. And the 3 is a vertical stretch. The 2x is a horizontal shrink. Okay, that's why we're at pi eighths now rather than pi fourths. So it's a horizontal shrink, a vertical stretch, and a reflection across the x-axis. Does that make sense? And if you look in your book, you see their drawing is almost as pretty as mine, but not quite. Okay? And of course, there is a checkpoint following every example. Okay. Now we're moving back to the PowerPoints. If I can get my pen to show up somewhere here. There it is. Okay, let's go back to, we should have 14 students here. Let's see if we do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've lost a couple more, one more. So let's go to 4, 6. Okay, and we'll go back to current slide. Okay, that was example 1 we've already done. Now we move to graph of the cotangent function. Now, the cotangent function for some reason always gives me a little more difficulty than tangent. Tangent sort of makes sense. Cotangent I have to stop and think about. But if you use the same procedure, it'll make sense too. Okay? The graph of the cotangent function is similar to the graph of the tangent function. Now remember, most of the time tangent is always increasing, unless it's a negative in front and then it was decreasing, just like we saw in the last example. Cotangent function, though, is a decreasing function most of the time, unless it's negated and then it becomes increasing. So that's one thing. That throws me off a little bit. The graph of the cotangent function is similar to the graph of the tangent function. It also has the period of pi. Those are the only two trig functions that normal period is pi, not 2 pi. However, from this identity, y is equal to cotangent x, which is cosine over sine, now the cosine is not defined everywhere that sine is 0. Well, where is sine 0? 0, pi, 2 pi, 3 pi, negative 2, at the whole pi's. Okay? That's where sine is 0. That's where cotangent has vertical asymptotes. So you can see that the cotangent function has vertical asymptotes where sine is 0 or any n pi, where n is any integer, positive or negative. So at the whole pi's, that's where the cotangent has the vertical asymptotes. Tangent was at the half pi's. Cotangent at the whole pi's. Now, the graph of the cotangent is shown below, and note that 2 consecutive vertical asymptotes of the graph are found at 0 and pi. Okay, now that's how they do it. I do it this way. Put my vertical asymptotes in at the whole pi's because that's where sine is 0. So write in the vertical asymptotes. You don't have to solve any equations for it. You know where they are at the whole pi's. Halfway between the whole pi's, at the half pi's, that's where your intercepts are. Now here's what I have to remember because I always tend to draw them backwards. Remember, in the first quadrant, between 0 and pi halves, everything's positive. So therefore that has to be going to positive infinity. At the quarter period, pi quarters, cotangent is 1. And at 3/4, it will be -1. So there again, they don't say anything about your intervals being quarter periods. I say do that. Well, that's where your plus or minus a's are. The plus a is in the first, so cotangents are usually decreasing functions. Okay, period is pi. Domain is all values of x except your whole pi's. The range is from negative infinity to positive infinity, just like tangent was. The vertical asymptotes are at your whole pi's, and your symmetry is about the origin. It too is an odd function. They don't say it here, but it is an odd function. If you go slightly to the right here, you'll go up, same distance to the left here, you go down the same distance. So it's an odd function, just like tangent. Well, guess what? It's a reciprocal of tangent, so if tangent's odd, cotangent's odd. Okay. That's how we do it. The only thing they left off is break it into intervals, and at the intervals is a quarter of a period. A quarter of a period, you're going to have your +1 or plus a and minus a. Okay, this one just happened to be a 1 there, so +1 and -1. Okay, and that will give it to you. So let's sketch the graph. Let's make sure I'm on the right one here. Yeah, example 3. Sketch the graph of this. Okay, and again, before I start sketching, I start figuring. Okay, and let me see if I can find my pen. Here it is. Your A here is equal to 2. Remember, tangent and cotangent and later secant and cosecant don't have amplitudes. However, the A is important. The book doesn't make much sense out of it, but it is important. Okay, it's where your quarter or your first interval, your quarter periods, that would be at plus or minus a. Okay, the value will be. Here your B is what? 1/3. What does that mean? The period is related to B by the normal period, and since this is a cotangent, that's going to be pi, not 2 pi like it is for sine, cosine, secant, and cosecant. Okay, pi divided by 1/3. Pi divided by 1/3 is the same as 3 times pi. You divide by 1/3, you multiply by 3. 3 pi. And again, our C is 0, there is no phase shift, and the D is 0, there is no vertical shift. I like to put those down too, just to remind me. Okay, so let's start sketching. Once I get the period, I do the interval. The interval is 1/4 of the period, and the period is 3 pi. So this is going to be 3/4 pi. That's going to be my interval on the x-axis. Okay, that's my ugly vertical line. Here's my ugly horizontal line. Okay, they're nowhere close. All right, my intervals are going to be here. 1, 2, 3, 4, 5, 6, 7, 8, -1, 2, 3, 4, 5, 6, 7, almost 8. Up here we'll go 1, 2, 3, 4, 5, 6 maybe. Down here we'll go -1, 2, 3, 4, 5, 6 maybe. Okay, let's put our scale in. Our intervals are 3/4 pi, so this will be 3/4 pi. This is going to be sort of awkward. This will be twice that, would be 3/2 pi. Okay. Let's double that, and you have 3 pi. And so that's 1, 2, 3, 4 make 3 pi. 1, 2, 3, 4 makes 6 pi. Going in the opposite direction, -3/4 pi, -3/2 pi. Double that, and you have -3 pi. And if we had enough to double that, it would be -6 pi over there. Okay. Now, scale here. Your A is 2, so let's just keep this 1, 2. I want to make sure the 2 gets on there. 3, 4, 5, and 6. And this will go down -1, -2, -3, -4, -5, and -6. Okay. There is no phase shift. Where does cotangent begin? At 0, vertical asymptote. Now I wish I wasn't in red here because I like to do my vertical asymptotes in red, but I'm going to do a dotted line here anyway. That's my vertical asymptote. And then I go 1 period over, and 1 period is 3 pi. So here's my next vertical asymptote at 3 pi. And another vertical asymptote at 6 pi. Get those babies in place. Okay? And another one over here at negative 3 pi. And if we had room for it, it would be at negative 6 pi, but it went off scale. Halfway between those vertical asymptotes is my intercepts. There, 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 and there. Now, halfway between those are my plus or minus A's. So this one's going to be plus 2 up here. This will be a minus 2 down here. A plus 2 up here. A minus 2 down here. I don't have room for that one. This would be a minus 2. If I could find my pen. Where are you, pen? There you are. Minus 2 right here. And a plus 2 right there. A minus 2 down here. And a plus 2 right here. Okay, from wherever that vertical asymptote was there, it's coming down. Twist a little bit here and then head toward the next vertical asymptote. Same thing here, coming down, twist a little bit and go to the vertical asymptote there. I didn't have my spacings too well, did I? Vertical asymptote here, coming down, twist a little bit and go down here. Same thing here, vertical asymptote coming down, twist a little bit there and go there. And if we had room, it would be coming down like that, and it goes behind. There's the graph of that. Now what have we got? Vertical stretch, that 2 is doing that. Horizontal stretch, because you're multiplying by a number less than 1, that's why you're stretched out to 3 pi rather than pi. Okay. And cotangent function is usually going downhill, decreasing function. Here's what I remember. First quadrant, here represented by right here, that's always positive, so you have to be there. Unless, of course, you had a negative 2 in front, and then it would be flipped over the x-axis, and that would be a minus. That's how we do cotangent. Any questions on cotangent? Okay, I'm going to clear my ink so you can see what they do. Alright, now they go to solving equations perfectly fine if you want to do that. 0 and 3 pi, we got it by doing your period. B was 1/3, the period is pi divided by 1/3, just like we did with sine and cosine, which is 3 pi. And once you get the period, just put them in there. Okay, you don't have to solve equations, but they're easy equations. You can do it that way, perfectly fine. You can see 2 consecutive vertical asymptotes occur at 0 and 3 pi. We got that by using your period. Between those 2 vertical asymptotes, plot a few points. Exactly halfway in between was going to be your intercept. And halfway between 0 and 3 pi is 3/2 pi. And that's where that was, of course. And halfway between there. And see, they do it but never mention it. At your quarter periods, you're going to be plus A and minus A. Why won't they say that? It makes so much sense to do it that way. At the asymptotes, of course, undefined, undefined. Okay. So I start off by just sketching those asymptotes, putting our dotted red lines in. They just don't do it on top of this one. I wish they did. And then plotting in the plus A here, the minus A there, the intercept there, and do the same thing every period, each cycle. Plus A, 0 minus a. You got it. Connect the dots. There you have it. Just like mine. Maybe a little neater, but not too much. Okay. Any questions? Example 3. How are we doing on time? I think we got 5 minutes. So let's talk about the graphs of the reciprocal functions. What do I mean by reciprocal functions? Well, cotangent was a reciprocal function. Sine and cosine technically are reciprocal functions too. What we mean are the reciprocal functions of sine and cosine, which are, of course, cosecant and secant. Because you can obtain the graphs of two remaining trigonometric functions from the graphs of sine and cosine, which we know so easily, then we'll do the reciprocals. So actually we don't really graph the cosecant and secant using anything special technique. We graph sine and cosine and then graph the secant and cosecant. For instance, at a given value of x, okay, the y-coordinate of secant is actually reciprocal of the y-coordinate of, secant is the reciprocal of the y-coordinate of cosine. And guess what? Cosine always stays between plus and minus 1. So that means secant is going to be outside of plus and minus 1. From plus and minus 1, up for positive, down for negative. Okay? Of course, when cosine is equal to 0, this secant is undefined, just like it was for tangent. So it's going to have the same vertical asymptotes as tangent. Okay? The reciprocal does not exist, and near such values the behavior of the secant function similar to that of tangent function, but maybe going in different directions. Okay? Goodness, I've been talking so long, my throat is drying out. Hold on. Need a little carbonation to break it up. In other words, the graphs of tangent x, which is sine over cosine, and secant x, which is 1 over cosine, have the same vertical asymptotes at all of your half pi's. Anywhere where cosine is equal to 0, that's going to be your vertical asymptotes. And those are usually going to be for just tangent x and secant x, no multipliers there. It's going to be at your half pi's. 1/2 pi plus n pi. Cotangent and cosecant are similar in that they are both, cotangent is cosine over sine, cosecant is 1 over sine. So everywhere where sine is 0, which is at your whole pi's, n pi, that's where your cotangent and cosecants are going to have vertical asymptotes at the whole pi's. So, to sketch the graph of a secant or cosecant function, you should first make a sketch of its reciprocal function, sine and cosine. That makes it easy. And for instance, the graph y is equal to cosecant x, first graph y is equal to sine x. We know what that is. Graph it. Okay? Then take the reciprocals of it and obtain the points for cosecant. And I'll tell you this, you basically only need 3 points this time per, well, I'll show you. Okay. So here's how you do it. If this is your sine function, sine starts at 0, goes up to 1 at pi halves, down to 0 at pi, down to minus 1 at 3 halves pi, back up to 0 at 2 pi, and just keeps on going. Same thing on the left, goes down to minus 1 at minus pi halves, back up to 0 at pi, minus pi, and then back up to plus 1. So you got it. So plot those first. Now, everywhere that sine is 0, vertical asymptote, because this cosecant is the reciprocal of that, you can't divide by 0. So everywhere that sine crosses the x-axis, everywhere you had a intercept for sine, put a vertical asymptote for your cosecant. Every time it crosses the x-axis. Okay? Then the rest of it is a piece of cake. At your maximum for sine, it's going to kiss cosecant right there, because 1 over 1 is 1. So cosecant's going to be there. When sine's going down, cosecant's going up. When sine's going down this way, cosecant's going up. Okay? It can't cross or touch your vertical asymptote, so it just makes this U-shaped shape here and goes up. Down here, it makes an arch shape shape. It touches at -1 and then goes down from here where sine goes up. Where sine goes up, cosecant goes down. And they just do that. They just go in opposite directions from there. They kiss at the max and min, and they go in opposite direction. Okay? Same thing for secant. Draw your cosine first. Cosine starts at 1, goes down to 0, -1, 0, +1. Everywhere cosine is 0, everywhere that crosses the x-axis, draw your vertical asymptote for your secant. And then the secants touch at the max and the min, and they go opposite directions from there. So if this is at 1, it goes up and up from there. If it's -1, it goes down and down from there. But can't cross the vertical asymptotes. That's how you graph them. No real points to plot except your sine and cosine. You plot those, and once you get those done, everywhere that either the sine or the cosine is 0, there's a vertical asymptote for the cosecant or secant. And then where the max is for your sine or cosine, that's going to be a local minimum for your secant or cosecant. Okay? And just go there. So the period is the same period as sine and cosine, 2 pi. Domain everywhere for, this is cosecant now, everywhere except where sine is 0, which is at your whole pi's. The range is going to be from -infinity to -1, including -1. So you block in the -1. And then starting at +1, so block in +1 up to +infinity. So it's not like tangent and cotangent, that's all real numbers. You start at ± -1 and go in the opposite directions. Okay? Vertical asymptotes are the same places where sine is 0. Okay? And the symmetric about the origin, because sine is symmetric about the origin. The secant function, do the same thing with cosine. Period is 2 pi because the period of cosine is 2 pi. Domain all real values x except your half pi's where the cosine is 0. Okay? That's going to be where you disallow. Let me make sure no one's trying to come in. I don't think they are. Okay. You disallow secant from having a value there because cosine 0. Then at the max and the min, those are the min and the max for secant. They touch and kiss there and then move in opposite directions. Okay? Always. So that's all you do. Plot the sine and cosine functions, draw your vertical asymptotes where they cross the x-axis, and then draw the curves from there. Touching at the max and min and going in opposite directions. Okay. I can't advance until I click on the slide again. Okay. Whoops, we've just gone over 3 minutes, haven't we? We're going to have to stop here and pick up here next time. Okay, we made really good progress though, but I have lost my pencil. There it is. Where are we here, Waldo? We're right at the bottom of page 311. Okay, so that's where we'll pick up next time. Let me erase my mark from last term that I taught this course. Okay, put my page in place, and let me give you some homework exercises. I think you can match all of 9 through 14. Now the answers are only going to be given for the odds 9 through 13, but I think you can match them all. Okay, but the answers in the back of the book and at Calc Chat will be only for the odds. Okay, I think you can even do secants and cotangents, secants and cosecants. Okay, though we haven't actually done those, so I would say in the next group, 15, 19, 27, 29, do those. They're all at Calc Chat, 19's at Calc View. Then in the next group, try to do 39, 43, 47, and those are all at Calc Chat. Go through and do the tangents and cotangents. Of course, Yeah, it's tangents and cotangents. You can try the secants and cosecants if you'd like. We just haven't had time to do them all. So we'll pick up and wrap these up next time. All right, any questions? Sorry I ran over, but guess what? There'll be no extra charge today. So any questions? I'm going to stop sharing. I'm sick and tired of sharing. Okay. Then what we'll do, if there are no questions, we'll end the meeting for everybody. So have a good, safe weekend. Of course, what will make it good is working on those research paper, working on your test, working on your homework, working on trig. That'll make it great, won't it? So take care. We'll see you Tuesday. Any last thoughts? Bye-bye.